A cosmic flash, brighter than entire galaxies yet gone in a millisecond, ripped through the void in March 2025. For years, fast radio bursts like these have defied explanation, outshining the sun's energy output for days in the blink of an eye, then vanishing without a trace. But this time, the universe's loudest radio scream was caught and traced with absolute precision. Astronomers called it RB Float, the radio brightest flash of all time. And for the first time, the James Webb Space Telescope has zeroed in on its exact home in the cosmos. This moment didn't just answer a century-old mystery, it shattered it wide open. What could create such a violent outburst, and what secret now waits in the glare? In 2007, a single flash hidden in old telescope data stunned astronomers. Duncan Lorimer and his student, searching through records from the Parkes Radio Telescope in Australia, uncovered a radio burst that lasted less than 5 milliseconds. In that instant, the burst unleashed more energy than the sun emits in 3 days. The signal, now called the Lorimer burst, arrived from far beyond our galaxy, its radio waves slowed and stretched by a thick fog of electrons, evidence it had crossed billions of light years. Nothing in the Milky Way could explain such power in so brief a moment. The discovery was so unexpected that many dismissed it as interference from Earth. Yet the numbers held. The burst's intensity, measured in Janskis, was off the charts for a cosmic event. Its brevity, thousands of times shorter than a blink, meant that even the most sensitive telescopes could have missed it unless they were looking at the right patch of sky at the exact right time. For every 1,000 hours of data, perhaps a single such flash would appear, and then only for a millisecond. As more bursts surfaced in subsequent years, a new class of cosmic phenomena took shape: fast radio bursts, or FRBs. Each one, brief as a camera flash, carried the hallmark of extreme energy compressed into a timescale so short that traditional astronomical instruments were all but blind to them. The challenge was not just their rarity, but their unpredictability. No pattern, no warning, just sudden outbursts from the deep sky. The sun, by comparison, shines steadily. A typical FRB, in just a moment, can outshine the sun's radio output for days. Early searches were like chasing lightning with a pinhole camera. The fleeting nature of FRBs forced astronomers to rethink their tools. Ordinary telescopes designed to track slow-moving phenomena were ill-suited to catch these cosmic bolts. What was needed were wide-field, high-speed instruments capable of scanning vast stretches of sky and capturing events lasting less than 1,000th of a second. The mystery deepened with each new detection, and the hunt for their origins began in earnest. The universe was speaking in a language of power and brevity, and for the first time, humanity had caught a whisper. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, was never built to chase cosmic fireworks. Its original mission was to chart the slow drift of hydrogen through the universe, mapping the expansion of space itself. But as the telescope's 4 enormous cylinders scanned the sky above British Columbia, its digital heart was quietly rewritten. A new generation of astronomers, led by Victoria Caspi and software architect Kendrick Smith, transformed CHIME into the world's most prolific hunter of fast radio bursts. Each day, the telescope's 1,024 beams swept the heavens, sifting through billions of data points for the telltale signature of a fleeting radio flash. On March 16th, 2025, the system flagged something extraordinary. At 0833 UTC, a signal erupted so bright that the automated filters, trained to ignore earthly interference, nearly discarded it as a false alarm. Amanda Cook, a postdoctoral researcher at McGill, was among the first to examine the data. The burst registered over 1,000 Janskis at its peak, saturating the detectors and leaving a sharp, unmistakable trace across the frequency band. It lasted just 0.2 of a millisecond. In that instant, the event, catalogued as FRB, 2250-316A outshone the combined radio output of billions of stars. The CHIME team would soon nickname it RBF LOTE, the radio brightest flash of all time. CHIME had seen thousands of fast radio bursts in the years since its retooling, but nothing on this scale. The burst's intensity demanded closer scrutiny. Standard analysis revealed a dispersion measure of 161.8, hinting at a source far beyond the Milky Way, but closer than the vast majority of FRBs. Its spectrum was clean, its polarization nearly perfect. Most telling of all, the burst's profile split into two sharp components, each with its own scattering tail. A fingerprint unlike any previously recorded. The sheer brightness of RBF LOTE posed both a challenge and an opportunity. Its overwhelming signal could be used as a beacon, allowing CHIME's new outrigger telescopes, scattered across North America, to triangulate its origin with unprecedented accuracy. For the first time, the network's full power could be brought to bear on a single, record-breaking event. The hunt was on to pinpoint the birthplace of the universe's loudest radio scream. Across North America, a network of radio telescopes stood ready to test the limits of astronomical triangulation. The CHIME outrigger system, now fully operational, connected British Columbia, West Virginia, and Northern California with the main CHIME array, forming baselines that stretched for thousands of kilometers. At the core of this system, each outrigger station was engineered with dual polarization feeds and precise digital backends, mirroring the design of the main telescope but scaled for rapid, coordinated response. When FRB 2025-0316A erupted, the signal arrived at each station at slightly different times, differences measured not in seconds but in billionths of a second. To achieve this level of precision, engineers had synchronized every clock in the network to within 30 picoseconds, using hydrogen masses and GPS-disciplined oscillators. This timing stability meant that even across a continent, the arrival time of the burst could be tracked with the accuracy needed to resolve angles of just tens of milliseconds. Each station recorded a full baseband capture, preserving the raw voltage data for later correlation. The analysis began with a search for the geometric delay, the tiny but measurable lag in signal arrival caused by the vast distances between stations. For a burst lasting only 0.2 of a millisecond, the system's ability to compare arrival times with such fidelity allowed astronomers to convert time delays directly into pinpoint sky coordinates. The result was a localization ellipse just 68 milliseconds across, corresponding to a physical region of only 45 light-years at the distance of NGC 4141. This degree of accuracy, equivalent to spotting a coin from nearly 100 kilometers away, was achieved by combining the independent timing measurements from each baseline, cross-referencing the burst's position relative to a ring of international celestial reference sources. Atmospheric effects, instrumental delays, and calibration uncertainties were all accounted for, with real-time corrections applied to ensure that every nanosecond counted. With these measurements, the CHIME outrigger array traced the burst to a single patch of sky within NGC 4141, shrinking the search area from a galaxy to a stellar neighborhood. The ability to achieve such precision transformed FRB localization from a statistical exercise into a forensic science, setting the stage for the James Webb Space Telescope to probe the environment with unmatched clarity. The era of continental triangulation had begun, and with it, a new standard for cosmic detective work. Within days of the CHIME outrigger localization, the James Webb Space Telescope turned its attention to a pinpoint in NGC 4141. The near-infrared camera, NIR-CAM, began a series of deep exposures, each one carefully dithered to sharpen the view of a region just 45 light-years across. Astronomers targeted two extra-wide filters, f150W2 and f322W2, spanning wavelengths from 1 to 4 microns. Over 9,400 seconds of exposure, the detectors gathered faint photons from the spiral arm's outer edge, searching for any sign of a stellar culprit. Near the center of Webb's infrared field, a dim source appeared, catalogued as NIR-1. Its position lay just 40 milliseconds from the FRB's radio centroid, well within the margin of error. NIR-1 was the only object in the area statistically consistent with the burst's origin. Photometric analysis ruled out a globular cluster or a young, massive star cluster. The source was too faint for a red supergiant, too bright for a lone magnetar. Its colours and brightness pointed to a red giant star, possibly near the helium-burning clump, or perhaps a massive main sequence star exceeding 20 solar masses. The latter seemed improbable given the brief lifespans of such giants. No evidence of a supernova remnant or nebular emission clouded the view. Instead, the infrared light suggested an evolved star, likely accompanied by an unseen compact object, a neutron star or magnetar. The surrounding field, resolved into hundreds of stars by Webb, showed a population rich in young, blue stars and a nearby H2 region, hinting at recent star formation. The FRB's location, offset from the heart of the cluster, matched models in which a young neutron star is born in a stellar nursery, then drifts outward over millions of years. For the first time, astronomers could tie a non-repeating fast radio burst to an individual stellar system. The implications ripple outward. Magnetars, long suspected as FRB engines, now stand on firmer ground. Yet the presence of a red giant companion raises new questions about binary evolution and the role of stellar interactions in triggering these cosmic flashes. With NIR-1 as a guidepost, the Webb team prepared for a broader campaign, future bursts, future targets, and the prospect of mapping the universe's most fleeting signals to their exact stellar homes. The era of cosmic forensics had begun, and the search for new origins was only accelerating. On March 16, 2025, the CHIME telescope recorded FRB 2025-0316A RBFLOAT, the brightest fast radio burst ever detected, with energy equivalent to what our sun emits in 3 days, released in under a millisecond. For the first time, CHIME outriggers and the James Webb Space Telescope traced an FRB to a precise 45 light-year region within galaxy NGC, 4141 130 million light-years from Earth. Webb's infrared imaging revealed a red giant or large star at the site, raising new questions about whether magnetars or binary systems produce these powerful flashes. While scientists now know FRBs can be tied to individual stellar systems, the exact engine behind RBFLOAT remains unidentified. This breakthrough proves that FRBs are not random, but have traceable origins, marking a turning point in astrophysics. As new campaigns combine radio and infrared data, researchers are one step closer to decoding the universe's most intense signals. The search continues, grounded in evidence and driven by the mysteries that remain.